Hello and welcome. My name is Nehadeep, and today we're going to talk about Windows Memory Management Fundamentals. When we talk about Windows Memory Management, uh, we can categorize it basically into two buckets. One is the physical memory, which is the RAM and the hard drive, and then we have virtual memory, which is, well, virtual, right? So we'll talk about both of them in a while. If you are from a IT background or if you're an IT professional, you must have heard about these two terms, right? 32-bit and 64-bit. So a 32-bit application can run both on a 32-bit OS as well as a 64-bit OS. But a 64-bit application can only run on a 64-bit OS. Similarly, a 32-bit operating system can run on a 64-bit hardware as well as a 32-bit hardware. But a 64-bit operating system can only run on a 64-bit hardware. Now, what is the main difference between them? One difference is a 32-bit application can access max 4 GB of memory, which is 2 to the power 32. Whereas a 64-bit application can access, at least in theory, 64 2 to the power 64, which is 16 exabyte of memory, which is huge. You're never going to need that much of memory in a one process, right? So if you are running a 32-bit application, maybe it's a 64-bit OS or a 32-bit OS, and you try to load a lot of data, you sometimes get an out of memory exception because it has exhausted all the memory. But you never see that exception, especially in 64-bit applications. So this 4 GB or 16 exabyte memory that we're talking about is actually virtual memory, not physical memory. So when I look up in the internet, I see a lot of misleading concepts regarding the 64-bit and 32-bit architecture. People says that it is 4 GB of RAM, which is not entirely correct. So that's the reason I thought of creating this video so that I can clarify what it actually means. This 4 GB memory that we're talking about in 32-bit, it cannot entirely be used by the application. Half of it is allocated to the user mode, which is exclusively used by the application, and half of it is used by the kernel. In your operating system, we have user mode or kernel mode, right? Some of the very important modules which needs high privileges, they run in kernel mode. For example, the file system itself, device drivers, hardware abstraction layer, which we call as HAL as well, graphic drivers, Windows Manager, Power Manager, plug and play manager is also there. Similarly, another important module is memory manager. So we'll talk about memory manager more in this session. Now, when a application runs, for example, you open a notepad and you just typed A, right? Just to accomplish this task of printing A in your notepad, it has to go through user mode and kernel mode multiple times. For example, when you press A in your keyboard, it interacts with the keyboard driver, which is running in your kernel mode, and then it goes to the user mode where the application needs to allocate the memory to store this alphabet A. Once that is done, it needs to display the letter in your monitor. For that, it again has to go through device driver, which is again in kernel. So any operation you do need to cross this boundary between user and kernel mode multiple times. So memory needs to be used on both the side. As I said, 2 GB will be used by kernel and the other 2 GB will be used by the application. Now, there are options where you can configure your operating system in such a way that 3 GB will be available to the process or the user mode, and 1 GB will be allocated to the kernel. It is done through a 3 GB switch. There's a switch called use large address aware. When so what it means is every process that runs on your operating system has its own 2 GB memory, considering it's a 32-bit process, and a shared 2 GB memory, which is the kernel. So what do I mean by that? Let's say example, I am running 3 applications, app A, app B, and app C. All these 3 will have their own 2 GB user mode memory, which it will use to store data. But all of them will use the same shared 2 GB kernel memory. So they have their own user mode memory and a shared kernel mode memory. Remember, I said that we'll talk about Windows Memory Manager in the later section. So what is virtual memory and what is Windows Memory Manager? When an application needs to allocate memory, it goes to the Windows Memory Manager and asks for the memory. It will create or allocate memory for the process and returns the virtual address to the process. For the process, it has no knowledge about the physical memory or the RAM or hard drive. It only knows the virtual memory, which is this 4 GB or 16 exabyte that we're talking about. These are all virtual memories. Now, when it needs to read the data from the virtual memory, it again goes to the Windows Memory Manager SA and says, hey, this is the virtual address, and I need the data from this address. The Memory Manager keeps a map between the virtual memory and the actual physical memory. So when it gets the virtual memory address from the process, it checks the map and sees where in the physical memory is the actual data stored. It fetches data from the store and then returns the data to the process. So basically, the Windows Memory Manager does address translation between the physical memory and the virtual memory. And when we say physical memory, it's not always the RAM. It is also the hard drive. So if an application is requesting, for example, 5 MB of space, the Windows Memory Manager checks if the space is available in the RAM or not. And if it sees that the RAM is quite busy right now, it doesn't have enough space available, what it generally does is it swaps some of the memory from the RAM to the hard drive. So it has its own logic to figure out which segment of the memory it should swap with the hard drive. But what happens is it creates a file called pagefile.sys. Generally, that's the name in the hard drive, and swaps the data from the RAM to this page file to free up some memory in the RAM. And then it will allocate that 5 MB of space that is just requested by a process in the RAM. I'm not going to go deep into it, but if you have heard about something called page faults, there are hard faults, soft faults inside that. So this is when those things happens. So when a process asks for some data from a specific virtual memory to the Windows Memory Manager, it first goes to the RAM to check if the data is available there or not. If the data is available, it simply returns it. If not, that's when a fault happens. That's when a page fault happens. and then it needs to go to the page file uh, to check for that data and fetches the data from the page file and returns it to the process. So that's how your application actually interacts with the physical memory. It is done through virtual memory and Windows Memory Manager. Otherwise, the process is not aware of the physical memory whatsoever. I hope the concept is clear now. Now, what is this magic number 32 or 4 GB? Why is it 32 exactly? And if it's 32, why can't it use more than 4 GB? What is the limitation? What is the restricting factor here that it cannot use more than 4 GB? So let's talk about that. So to do that, we need to dig a level deep and talk about how it works in the hardware layer, mainly your processor. So your processor can be 64-bit processor or a 32-bit processor, which is mainly the restricting factor of your OS and your application. You cannot have a 64-bit OS on a 32-bit processor. The other way would work though, right? So how? So to do that, uh, so this 32-bit or 64-bit refers to the number of bits which would be processed or transmitted in parallel. I know it's not super clear, right? So let me explain. So let's say, for example, we have the processor here, right? So in the processor, there are a lot of bus, or you can call it to simplify, group of wires that goes out and comes in into the processor, right? There are service bus, there are address bus, etc., etc. So here we're talking about memory, so we'll talk about address bus. So when we say 32-bit processor, what it actually means that there are 32 lines in that address bus. One line, you can um, think of it as one where, right? And if you know a bit of binary, you know that it's all 0 and 1. So a where can either be 1 when it's on or electrons are passing through it, or it can be off when there is no electrons are passing through it. So one where or one line can have two states, right? 0 or 1. 1 is when the electron is passing, 0 is when nothing is passing. Now, to understand this concept of 32 GB and how is it related to 4 GB, let's simplify the concept. Let's say, for example, instead of 32 GB, I am talking about a, 32-bit, I'm talking about a 2-bit system, right? So that means there are two lines going out of your processor, right? This is the processor, P, and there are two lines. Now, both these lines can either be 0, off, or 1, on. Now, if that is the fact, then what are the different combinations possible for a 2-bit system? Both the lines can be off, which is 0, 0, 1 off, 1 on. The first one is on and the other one is off, or both of these are on, right? 1, 1. So these are the these are the four different values that it can store, right? It cannot store anything other than these four. So it is limited by 4 address that it can address now, or it can refer. Now, let's say, for example, these are memory locations, right? 1, 2, 3, 4. Each memory location has an address. For example, let's say the address of the first one is 0, 0, and then 0, 1, 1, 0, 1, 1. So if this is it, then this processor can easily refer to all these addresses through its 2-bit architecture, right? But if there is another memory location like this, which let's call it 001. At a time, it cannot refer to the fifth one, right? Similarly, and why is this 4? So if you can want to calculate, it's 2 to the power 2, which is 4, right? So these are the 4 addresses that it can refer. Similarly, for a 32-bit processor, there will be 32 such lines going out. So that is 32, I'm sorry, that is 2 to the power 32 equals to 4 GB. Now, if we want to calculate it, let's say, for example, um, let's do the math. 2 to the power 32 equals to this big number that is coming up, right? So this is bytes, because each of this box, if you see here, 0001, those or each of the memory location can store 1 byte of memory, right? So this many byte it can address. Now you know 1024 byte equals to 1 KB and 1024 KB equals to 1 MB and so on and so forth, right? So let's divide this by 1024. So this is a KB. Divide by 1024 again. This is the MB. Divide by 1024 again. And this is the GB. So it's 4 GB. So that's how this 32-bit architecture can refer to 4 GB max. And the same math you can do for the 64-bit as well. It's the same fundamentals. But though logically or theoretically 64-bit can address the huge amount of space, but in practical, today's operating system, especially Windows, don't use the entire 64-bit. It's probably use something around 48 bits out of those 64, which translates to around 256 TB, I guess, 128 TB for user mode or 128 TB for kernel mode, around that. I don't remember the exact numbers, but somewhere around that. Because it doesn't need to, it's already too big and it's sufficient to address today's application, today's challenges. So guys, I tried to simplify it as much as possible, but if you have any questions, if you have any confusion, please reply in the message below and I'll try to respond to your queries. Please subscribe and like the video, and next time I'll come up with another interesting video. Till then, thank you and goodbye.